Hello everyone, how's it going? Welcome to this course on self-driving, and on the first chapter we are looking into perception, which is all about developing these computer vision algorithms that can understand the lane and detect where the lane is moving towards. So this is all about making computer vision algorithms that can do the job of visual perception for us. Now, this is the first stage where we're going to try and develop a simple lane detection system with nothing too complications, just understanding the basics. Now, you can go into Google. We're going to be using Colab for this purpose, so we can run it. So let's go into Google, just search in Colab, and it will take you to something like this. So click the first link, which is Google Colab right here, and it will take you to something like this. Now, once you're here, it allows us to run all the Python applications here in the browser itself, taking care of all the dependencies. In fact, it does provide us with 3 GPUs, which we'll be using in the future stages, and hence we're going to be trying and running it in the Colab. Now, first step is I have this video file test1.mp4, and we will try to use this, and I'll put the link in the description so that you can copy it yourself as well. Let me download this. I just copy the address so I know where the file is, and I come here and I try to download that file so we can use the images from that video file for our test purposes. So the first step would be to download this file. I would say wget, but before that, let me maximize this a little bit so it's comfortable. I think that should be fine enough. So we're going to download this file. We say wget o 0, and then the file name, which is test1.mp4, and file download. So the file that we have, we're just providing the link, and we're asking Colab to download the file for us. So it will take care of the downloading aspect. And oh, you know what? This was the big O. So instead of 0, this is big O right here. Just press the play and it will download the file for us. And if you come into this particular file directory, you can see test1.mp4 is available for us to use. Okay, perfect. So now we don't need this guy. We come into and open up a new code file and start reading this. So the first step in this process is to do something called as Canny edge detector. So let's open up Google and try to understand what is this Canny edge detection. So this is the neat algorithm, very good algorithm, and it's very smart. What it does is it allows us to give an image, a colorful image, a image with all these information available in this, and it can extract the edges. So all the edges, it can pull it up and give it out to us. So it's very easy and makes things in order for us, our lane detection to detect the lines, it comes out very helpful. But looking at this, it's able to detect all the hair fibers here. The background is blurred, hence it's not able to detect any lines here, but it can detect all the features. So what this algorithm basically does is it looks into the gradient profiles and see where the color is changing. So you can see the hair and the background, which is the green, there is a contrast in that. So this contrast, it takes it as an edge and then gives out wherever these boundaries and wherever these edges are changing colors. That's how it pulls it up for us. So this is all about Canny edge detection, and we will use Canny edge detection as the first stage to detect all the lines available in an image. So before we go into all that, let's read the image that we have and try to see where the image is, so then we can start using it. So for that purpose, we will import OpenCV. You see import CV2, which is OpenCV, and Colab already comes installed with it, so we don't need to worry about it. But once we read OpenCV, now we can use OpenCV to read our test1.mp4, which is basically a image of a car going through the road. So we just read this image, we say, and OpenCV has this function, or consider OpenCV as a library. And this library has a book inside this library, which is called as video capture. This book allows us to read the video file. So we say, okay, capture. I'm going to create a variable called capture. And this capture variable will be responsible for reading the video file for us. So we say cv2.video capture. and this is the capture file, the function, and we just need to provide what the video file is. So we come here and then just copy the path from here, close this back again, and paste the copy path here. So we're just specifying that the file path is here. It should be as a string, so it will go and read the file for us. Once it reads through all the file, then you can use this capture variable to read individual frames in your capture, in your video. So for that purpose, we say frame equal to capture dot read. Very good. Now this also comes with a flag. This call is a ret flag or return flag. This is just specifying, this flag helps us identifying whether the capture happened perfectly or not. If there's an error, this red flag will turn into false, and you can then detect where the issue is happening. So it's just for debugging purposes, but the image from the video will be saved in this variable called frame. So let's try to display this frame in the browser and see how it looks. And for that purpose, there is a separate function in Colab that allows us to display the image in the browser itself. For that purpose, we say from google.colab.patches import cv2_imshow. So this imshow function can then show the frame for us. And we call those imshow function, we say cv2imshow function, please take our frame and then display it in the browser for us, so we can see how this frame looks like. So we can see that it has opened up this frame for us, and this is how the frame looks like. Now our idea is to identify where the lanes are present in this video. So the first step would be to do Canny edge detection. The Canny edge detection can help us identify where all these color gradients are, like this line, these lines, everything will be detected by Canny edge. So let's do that. So we have this frame function. Now the frame, this frame is basically the image that we are using. Now come down here, we'll put a new text here so we know what is happening. We're doing in this purpose, in this section, we're going to be doing Canny edge detection. Now, what is Canny edge detection? We saw how it is, but let's see how we can code it. So there is a simple function for Canny edge detection. Let's define a function called Canny, which can take an image, img, and then process the image and perform Canny edge detection for us. So we say, now the first step before we send it out to Canny edge detection, we need to make it as a grayscale image. And grayscale image is because this is a colorful image, and colorful image has a lot of information. It has a lot of, it also consists of 3 matrices or 3 channels, the red, green, and blue channel. And that's a lot of information for a Canny edge detection to handle. So this function, which is the Canny edge detector function, this function, which is already available in OpenCV, it can only work on grayscale images. So we first convert the image into a grayscale image. For that purpose, we do gray equal to cv2 convert color, and convert my image, which is the img image that I had, and convert that into a grayscale image. So originally, OpenCV has it as a, you know what, I have to put caps locks. It's color underscore BGR to gray. So what we are doing here is, originally the color comes up as a BGR. So OpenCV reads it as a blue, green, red variable. Now we are converting it into a grayscale image. So we're just saying OpenCV convert it into a grayscale image for us. Now there is a function called as cv2 Canny. So before we call that cv2 Canny, we need to do one more purpose. We need to change that. We need to change this into a grayscale image, and then once the grayscale image is done, then we need to blur the image. The reason we're doing blur is because this image is if it's very sharp, then it will detect all the erroneous edges that we are not interested in. Like these edges that we see on here, it will start detecting all these erroneous edges available, and these LNS edges are not helpful. If you come back to this image right here, this particular background, you can see it doesn't have any edges. The reason for that is because it is blurred, it is very blurry, and it's not able to detect any edges in there. It's very hard for the algorithm to see any kind of color contrast because it is blurred. And for that purpose, we'll blur this image a little bit as well. And for that purpose, we need to first specify a kernel of size 5. So it's just the window size which the blur variable will be using. And we say blur equal to cv2 underscore Gaussian blur. So there is an OpenCV function called Gaussian blur, and we supply the image gray, and we say please make it into a blurry image using the kernel size of 5 by 5. So this is a window which is a 5 by 5 pixel, and this 5 by 5 pixel will go through the whole image and then convert it into a little blurry image. Once we specify the blurry image, then we use this blurry image to do Canny edge detection for us. So we say Canny equal to cv2 underscore Canny, and then we need to specify the image that we have. So the image that we have is blurry, and for Canny edge detection, it needs to provide some threshold values. These are the threshold values just specifying the color contrast range that we are going to be using. And for that purpose, we'll say 50 by 150. You can play with these values depending on the image that you're working with, depending on the file that you're working with, but 50 by 50 should be working out pretty well. Once it does everything, then just return the Canny variable. That's all. So this function is going to do some Canny edge detection for us and then display the image. Okay, now let's open up a code, and in this code we will try to call this Canny function. So we already have the image from the previous function, from the previous code where we have frame. Now frame is nothing but this particular image that we have, and we will say output, or we say Canny output equal to Canny, this Canny function, and we are going to supply the image frame. Once it calls Canny, then it should display the image for us here in the browser. So we say cv2 underscore imshow Canny output. So let's try running this. First we will run the Canny function that we made. So it ran without any issues. Now we come down here and we supply the Canny function and see what kind of an output we get. So now you can see that it is able to detect all these edges, which has all the trees, which has all these roads and frames. Everything is being detected, and it's able to show where the Canny edge is available. So Canny edge detection is working fine. It's able to identify all these lane markings and everything else available here. So this is the first stage, detecting the lanes. Now we are only interested in the lines that are representing the lanes, and these lines are available here in this region, which is nothing but a triangle. So it looks like a triangle with one edge here, the other edge being here, and the third edge being here. And that's the triangle that we are interested in. We are not interested in all these shenanigans that is happening in the rest of the image. So all these trees, the other lane markings that are of no interest for us. We are only interested in the lanes that are available in the bottom region of the image. So for that purpose, we will create what is called as a region of interest. We're going to specify OpenCV, and we'll tell OpenCV, okay, OpenCV, very good job on the Canny edge detection. You're able to detect all the lanes, but I am only interested in this triangle. So please remove all the other extra edges that I am not needed. This is nothing but noise for me, and this will mess up my algorithm. So I'm going to remove everything else, and for that purpose, we'll create something called as a region of interest. Now come back here. We will, after this definition or after this function called Canny, we will create a new function called region of interest. Region of interest is equal to region of interest. So this function or region of interest or something called as ROI, it can take an image and then do the output for us. So again, you specify IMG, and this IMG image is going to help us give us the region ROI image. So the Canny image that we find in this step, we will supply it to the region of interest to get the triangle that we are interested in. So the first step we want to specify, in order for us to draw the triangle, let's identify what is the height and shape of this particular image. Then we can come down and reflect and understand where the triangle should be available. We say height of the image is given by IMG shape 0. And the width of the image is given by IMG dot shape 1. So this is specifying the height and the width of the image. Now we're going to create a new variable, a new function or a new variable called mask. And this mask is going to help us mask everything else and just focus on that triangle that we are interested in. We need another function or need another library called as numpy, and we say import numpy as np because we are creating a new image. NP, which is nothing but zeros, it's going to be a matrix of nothing but zeros, and this zeros and this function or this image should have the same shape as the original image that we supplied. So we are just creating a mask of nothing but zeros, and this shape of the mask should be look like our IMG image. Once we have this IMG image ready for us, then we start creating the triangle. The triangle is specified by 3 points. We need 3 points designing the triangle. So we'll start by that. We say np dot array, and now you're specifying a triangle, and for that purpose we will create a array, and the first point would be the location 200 by height. And what we're doing is now we're trying to specify each and every point here, every point of this. So this 200 by height is here. Then we are going to be slowly coming down and take out this point, which is roughly 1200 by height. And then this point, which is nothing but almost half of the image. You have whatever the size of the image is, it'll be half right here. In my case, it's coming out to be close to 800 or 300 region. So here, and basically the height is 350, and the width from here, it's about 800. So this point is about 800 from here and 300 from the top. So we will take that and come here. So the first point we specified is 200 by height, the first coordinate. Then you have the second coordinate, which is specified by 800 by 350. So these are just the coordinates of the triangle. And the third and last coordinate is given by 1200 by height. So this is the last coordinate which carried out. And you're just specifying all, this is just designing the polynomial for us. Once we have all of this defined, we just say that it is going to be an integer of 32 type, int 32. That's it. So that's the triangle that we have. Now what we will do is, this mask is initially of nothing but zeros. In that mask, we are going to create a triangle of this size that we specified here, of this size, and make that triangle itself of color white, everything else black, and this triangle looks white in color. So let's come back here and we say CV2 fill poly. So this fill poly or fill polynomial, so whatever polynomial, whatever range or whatever value you give, it will fill that polynomial with the color that you specify. So we say fill polynomial, and this image that we have called as the mask, please fill this image using this variable triangle. So wherever the triangle, the edges of the triangle are defined, please fill everything with that triangle with 255. 255 is nothing but zeros, or if a collection of 255 is nothing but white color, so it will give us white color triangle in that black image. So the masked image, now the masked image will be a bitwise operation, a bitwise AND operation of mask and the IMG image. So this IMG image that we have, it will then multiply with this mask guy, and wherever it is white, it will pass through, and wherever it is black, it will stop. So for that purpose, we will use OpenCV bitwise and this AND function will help us only select the region where the triangle is defined. And for that purpose, we say CV2 bitwise AND IMG using the mask that we created in the previous stage. And this returned masked image. That's it. So this function is just going to create a region of interest for us and specify that triangle. Once we have this, come back here, and now we will call another function. Once we have the Canny output, we say, okay, masked output equal to region, or this function. Let's copy this function so we're not making any mistakes. We say region of interest and use the Canny output that we had in the previous stage, and then display this image instead of the Canny output. Now you can display the masked output. Okay, so it looks good, and let's first run the region of interest. Come down here. Now let's run this section. So now we can see that all of a sudden, let me minimize this a little bit. So you can see all of a sudden, everything else is removed. All the edges that we saw earlier is removed, and we are only looking at the triangle that we defined here. There are still some edges that we can see right here, which we will remove in the next stages, but the majority of the noise is now removed, and we can now focus our attention on these lanes itself. So the region of interest took care of that for us. Now let's try to remove everything else, all the other lines and all the other error and noise that we see here. These all portions, these are all noisy information that we are not interested in. And for that purpose, now we have a function called as Hough lines. I don't know how we exactly pronounce this, but if you look into Hough lines or Hough transformation, this is another neat application or neat function, and very smart. So what it does is it is able to understand where the lines are. It's able to understand where these lines are, and it's also able to identify where these lines are projecting. So from our perception, now think about it as a human being. You can see that these are the lanes, these are the lines, these are where the lanes are looking up. But from a computer's perspective, it does not know that this is a line. For a computer, this is nothing but a set of pixels, white pixels, arranged in this fashion. It does not know that it is a line. It does not know that these are arranged in a fashion that goes in this direction itself, and only this direction. So a computer does not understand these as lines. It only understands it as a pixel. And that is where we take this function called as Hough transformation, where if you specify this region, and it will read through all the pixels, and it will try to find a pattern. And in that pattern, it can then see, okay, these white dots seems to be arranged in this fashion, and they're going in this direction. So it must be something like a line. So that is what a Hough transformation does for us. So it goes through a region of pixels, and then tries to understand what kind of an image is it. Is it a line? Is it a circle? Is it a polynomial? Whatever it is, a Hough transformation can predict the shape of the pixel or where the pixel is going, and then identify these shapes within an image. And for that purpose, there is a function in OpenCV called as Hough line transformation. Hough lines transform. and we will call this function called as definition Hough lines. So this Hough lines can take an image and then identify where these lines are present. Again, we will say img. Okay, very good. Now we are also going to specify a image, and we say Hough lines equal to, so these Hough lines are basically the lines that we will obtain from this image, and we will use those Hough lines now. We specify the image img, and now this function cv2 dot Hough lines p. There are different types of Hough lines that we can use. This Hough lines p seems to be working very nicely. Hough lines p, and then we specify the image img, and it has certain other functions. This rho, the theta, the threshold, these are all filter variables that we can use to fine tune the function. So if you see that it's missing any kind of a line, or one of the lines that it should have originally detected, it's not detecting, you can fine tune these values to then identify where these functions or how this Hough line transformation should be working. So we specify Hough lines, and 2 is one RHO that we will use, and then we will use NP, or the pi, divided by 180, all the threshold variables, and then another 100. You don't need to worry about these are just specifying whatever variables or whatever values that we are using. Then we have an array. We want to please give me an array of all these lines, how these lines should be looking like. It's going to be a blank array for now, but you're going to be letting us know how this look like. And now I'm also going to let you know that the minimum length of my line, or minimum line length, is going to specify by maybe a size of 40 pixels. So what it does is everything, any line which is less or more less than 40 pixels, like probably this line or this line and all these lines, it's going to ignore that, and it's only going to focus on these big lines which are available here. The minimum length of the line is 40, okay, which is good, and the maximum line gap is expected to be 5, maybe 5 or 10, whatever you specify. So you're just specifying some of the features that we know about the image, and once we know all of that, we just return Hough lines for us. So this Hough lines is nothing but it's going to be an array which will have all the location of the points or the coordinates of the lines. So we just run this, and it looks like we have an error because we did not write the spelling of return. Oops, return. So it's able to return all the Hough lines, whatever Hough lines that we specify. And for us to obtain these Hough lines, we just create a function called Hough lines, and call this function Hough lines, and we supply the image that we found in the previous step, the masked output. So once we call this, it will just create or obtain these lines. If we run this, lines are nothing but it's not an image, it's all coordinates, and in the next stage we will try to then draw these lines on our image. And for that purpose, we will use one of the OpenCV CV2 draw line functions, which will help us line or draw the lines for us. So let's come down here and try to understand how we can then draw the image or draw the lines for us in this function. So come down here, open up another code, and once we have the line segments, then let's draw the line for our cells. We will define this function called as display lines. So this function will help us draw the lines that we detected in the previous stage. So display lines, and it can take an image and the lines that we detected in the previous stage, and then use that to draw the lines on our image. So let's call it a new image, or let's create a new image. We will call it as line image equal to np dot zeros like image Yeah, this image or this image, this image. So it's creating another zero image of of the shape and size of this img image, and then we will go through each line. And so these lines are nothing but coordinates of line segments, and it will go through each line and draw the lines for us. So we'll say if line is not, or lines is not none, so only if the lines are available, then go ahead and read through all the lines for line in lines. Please go ahead and read through all of them. So the lines are specified by x1, y1, x2, y2 equal to line dot reshape 4. So it will go through each line segment inside that lines, and then each line segment is going to be specified by 4 points, x and y1 for point 1 and x2, y2 for the point 2 of that line. Now using these x1, y1, x2, y2, then we will draw the line segments. OpenCV has this function called cv2 line, and it can take the image that we specified, line image, and you can draw the function x1, y1, okay, and we can draw x2, y2, okay, good, and we can then specify 255 /0/0. This is going to be a red color line, and we're just specifying that this is the color of the line, these are the points of the line, and the thickness of maybe 10. Okay, once we have all of this, we just return the line image for ourselves. So it's defining the line image. So what we do is we come down here. Now we will call this display line function. We say, okay, image or line image equal to display lines, and it's going to take the image that we have, or we specify the masked output, and we specify also the lines that we detected in the previous step of the Hough transformation. And using that lines image, we now just specify, or we just simply draw the image. So let's come down and run this. Oh, you know what? We did not run this step first. We need to first run the display lines and then come and run this line. So it's not detecting this because we are still showing the masked output. Instead of the masked output, we want to read and show the line image. So we can see that it's showing this color, or this black and white image, which is the masked image. And in that image, we are specifying that these are the locations of the lines that we found. Now, the reason we are seeing it as a white color is because we are sending out this zeros like image, and the zeros like image is nothing but it's all full of zeros. Now, instead of zeros, if we were to do instead of the zeros function, if we specified, and instead of the img function, if we gave the frame, for example, so like instead of the masked output, if we were to send out frame, and instead of the display lines, or let me comment this, and we just copy this function or this line again, and instead of drawing it on the black image, if we draw it on the main image itself, we can say draw it on the img image. This img will be the frame, the original frame. And let's run this, and let's run this, and it's going to be in the line image. Oops, it's black and still black in color. The reason why it's coming out as a black in color, we're specifying the line function here. We are having the display lines. Our display lines is taking the frame, that the original frame that we have. It's also taking the lines, and it's going to draw an image for us. And we are drawing the img function, the x and y1 coordinates, and it's going to specify or send the return line image. So instead of returning the line image, we should be returning the img image. Come back here, run this, and run this, and now we have a image with all blue color, all these edges that are detected by the Hough transformation. Now, at this point, we are able to detect, have a rough idea of where these lanes are present. There are still multiple detections which are not of any concern for us, and it can detect. It's detecting multiple lines here instead of one lane, so it's detecting multiple lines. But we want to be focusing both these two edges as one edge. So this is one edge and this is the other edge. That's how the Hough transformation should be working. So for now, we get to the point that we are able to roughly identify where the edges are, and then we are able to specify. In the next video, we will see how we can clean this all matter and then focus on one edge on left and the one edge on the right. Yep. With that, see you in the next video.